Do you want to know why he's not texting you right now?
So I'm really into Pythagorean triples. I don't know why. I really like these triples. The Pythagorean triples being triples of integers that correspond to the sides of a right triangle A, B, and C, where all A, B, and C are integers, and this is a right angle, such as the 3, 4, 5 triple. And in particular, I'm really interested in these triples that differ by one, that the hypotenuse is just one more than one of the sides. So for example, the 3, 4, 5, the 5, 12, 13, here 24 and 25, here 40 and 41. Not all of them are like that, but some are like that, and those correspond to triangles that are very skinny. And this side is just one less in length than the hypotenuse. So you might wonder, maybe that's just a few of them, or maybe there are infinitely many. How do we tell? Well, in a previous video, I've proved that if the Pythagorean triple is primitive, meaning that all three coefficients are relatively prime, and if that happens, that this is one more than that, then these two numbers have to be relatively prime, so it's primitive, then it's given by this formula for some other integers m and n. And then if they differ, if one of the sides differ from this one by one, this one and that one, those are both odd, so they differ by 2 at least. So that cannot be it. So this one has to be the one that is less than the hypotenuse. So then you have the 2mn, that one, plus 1 is the hypotenuse. And then if that happens, then we can bring this to the other side and I get this expression, but that expression is a square. And if I just assume that m is bigger than n, then it has to be then m minus n is 1. So m minus n is 1, so m is n plus 1. So then if I plug in this formula, m equals n plus 1, then what I get is a formula for Pythagorean triples that satisfy what I want, that the hypotenuse is one more than one of the sides. And in fact, all such triples are of this form. And if I simplify these formulas, I get this simple formula for such Pythagorean triples. You can check that they do satisfy Pythagoras' theorem. And then by plugging n values of n, I can get examples. N equals 1, it's the 3, 4, 5. N equals 2 corresponds to the 5, 12, 13, and so on. And you can get more, and you can get triples with arbitrarily large coefficients just by substituting large values of n. For example, that one.